Hey guys, good afternoon. Here we go. It turns out space is really, really hard. I think probably everybody in this room understands that. It's particularly hard, I've found, when you're on ground. Like, you don't actually have to send things all the way up into space for it to be difficult. In particular, we already highlighted earlier, there was a presentation just 2 ago that highlighted the huge amount of capacity that's going up into space, right? We've got geosatellites with HTS capacity that have reduced the cost of high bandwidth internet access by more than a factor of 100. We have LEO satellites that are bringing that down even further, leveraging what is actually about 5,000 times more spectrum resources than exists for terrestrial mobile applications. And this is not really a presentation about that, but it's worth taking 2 seconds to think about that. 5,000 times more spectrum than is available to the terrestrial wireless industry that is a $1 trillion industry today. Holy cow. So there's a huge amount of capacity up there. And there's also all sorts of new production methodologies and things happening on the ground, new technologies that are coming around all the time. In our case, we use liquid crystal display production, and so you see on the bottom left, liquid crystal display. A different company might have CMOS or other things that are happening. And you'll see business plans that look a lot like this. We're not the only ones, but you'll see business plans that look like this, where you see, okay, lots of throughput, new technology, choke point. We got to actually land that. We got to get that to the ground in order to start addressing this tremendous growth in the need for mobile capacity. And so that's what I'm going to talk to you about today, but this is not a business pitch. What I really want to talk to you about is how hard that is. And what it actually looks like to go through the Edisonian process of trial and error and error and error, and how that really comes about and what it's taken, at least for us, to get to commercial realization. So this is a brief history of Kymeta. It is also a story of how I got this really cool polo shirt, and I'll get that at the end. All right, this is the very first electronically scanned antenna we ever made. And the whole thing started with this vision of, man, we could do reconfigurable holographic metamaterials that are liquid crystal enabled. How cool would that be? No phase shifters, no gallium arsenide, gallium nitride in antennas, all sorts of things we could do. But first, we had to prove that we could just do some basic beamforming. Just 1D beamforming. Is it even possible? Do the physics work? And I did this work at Intellectual Ventures, and they thought I was crazy, to be honest. They're kind of like, right, reconfigurable holographic metamaterials. What could possibly go wrong? Why don't you try it out? So we tried it out, and the first thing we realized was with the design that we had, we couldn't actually make the darn things. We went to a PCB house, and we've got all these resonators. We're going to put liquid crystal on. It's going to be great. By the way, I need a 10-micron gold lead to slide in right here and provide a bias voltage. And they, of course, laugh at us. But I came from a semiconductor fab background. So I was like, well, if you're not going to build it for us, we'll build it ourselves. And we were at Intellectual Ventures Lab. I was like, guys, where's the clean room? Oh, there's no clean room. Great. How about a dark room? There's no dark room. Okay, what can I make dark? Turns out the only room we could use was the bathroom in the biolab. So in this 4-foot by 5-foot space, we actually built a little dark room and clean room fab. There wasn't very much ventilation there, and for any of you guys who have done semiconductor processing work, there's a lot of chemicals in the air. I'm much more fun to hang out with now. But this is where we started, right? So, we didn't have the garage startup. We had the bathroom startup, and we produced this, which was the very first electronically scanned antenna. Don't talk to me about the performance, but at least it showed a beam scanning. And then we made this. This antenna was very flat. It was only a couple millimeters thick. But the box of electronics that was required to control it was very large and very expensive to produce. But this was actually our first time doing 2-dimensional scanning. Well, that needed to go away, so then we moved on to an architecture like this. And this was the first time we went to a waveguide fed antenna. It's the first time we actually powered the whole thing with a USB cable, started to get up to appreciable performance parameters, and used this as the basis by which to launch the company in 2012. We called that Antenna 0. And we didn't really get very clever with naming conventions. So we went from Antenna 0 to Antenna 1 and Antenna 2. Our first product's Antenna U7. So that was great, but we built that by hand. In fact, that took a series of all-nighters to actually make even that M10-0 prototype. So we had to get to something that was more scalable, which meant process and iteration and starting to have some manufacturability that would allow us to make more than one of the darn things. And so we started doing that as a company and got to levels of performance that allowed us to connect to satellites for the first time. First on DirecTV in early 2013, and then on Anik F2 doing transmit and receive. So we were doing this all at Ka band, so 20 gigahertz and 30 gigahertz operation, which are pretty high frequencies. All of this done on these circuit boards actually turns out pretty expensive to produce. And this is what those systems look like. And we even did some NGSO tracking with these systems so we could track and hand off from satellites that were going across the sky. But this was too expensive to make, not commercializable. And even though we had to put in all this effort and learn so much about what to do, we realized we had to go back to the drawing board. And we ended up doing something like this. So instead of having these individual waveguides, we went to a different feed architecture, a cylindrical feed architecture now. And this was something that we could produce, and actually we could do what's called the dynamic polarization, which allowed us to address KU band opportunities. We built some of the first ones still using PCB architectures. And if you looked really closely at this panel, you'd actually see a little transistor on every single one of about 20,000 elements across that surface. So literally soldered on, still very difficult to make, but we managed to do some of our first mobile demonstrations and install our first antennas into cars. What's cool about this architecture, though, is that it's the exact same architecture that is used for a display. If you're looking at some of you are looking at phones right now. On every single pixel of that phone, there's literally a transistor just like this PCB cylindrically fed antenna has. And so the next thing we did was we went to Sharp's fab, and we literally started producing the active regions of our antennas on liquid crystal display panels. And that was the first time that we were getting them off of production facilities that were really representative of the $250 billion of manufacturing infrastructure in this industry. And we did the natural thing that one would do. So we got the very first ones off, we tested them, they worked, so we put them on a car and we drove across the country. This was a terrible idea. But it worked out. It was actually kind of cool. We actually came here in 2015. We drove across the country, did a whole bunch of stops, came and did some demonstrations, some mobile demonstrations here. Still not finally, not productized yet, but enough that we could show people. We thought that was a really important thing to do. 2016 was the year of beta development, so we really were trying to get all of the environmental implementations that were needed, meet regulatory masks that are necessary to actually operate these on a global basis. And then finally, in 2017, we reached commercialization. In fact, even just last year at this conference, I remember talking to people, guys, we'll have it, May. We're going to ship in May. And in fact, we did start shipping in May. Restricted availability, and then moved to general availability in December. A really difficult path. But our first commercial installation might have made it all worthwhile. Can you guys press play? So do you see our panels on top of this? This is actually the Maltese Falcon. This is a ship that was designed by Tom Perkins. He designed it not to have any satellite connectivity, and then when that became untenable, folks installed the mast and domes in the front. And so we're looking forward to getting rid of those. But they did a series of Atlantic crossings, and we're so happy that I was actually invited on board after the Monaco Yacht Show this past year and did a little tour around the coast of Italy. And I did so well that they gave me a polo shirt. And so that is the story of how I got this polo shirt. Look, at the end of the day, what I really wanted to share was that this stuff is hard. And I think there's probably a lot of people in the audience that are doing similarly really difficult things. And every once in a while, I think it's helpful to hear a story about somebody who's gone through the difficult Edisonian process of trying and failing and retrying and figuring it out, and then finally getting to market. So thank you very much.